Section 3.6, Derivatives of Logarithmic Functions. This is going to be similar to what we saw with derivatives of inverse trig functions at the end of the previous section. So first of all, we're just going to start with an understanding of logarithmic functions. So if we have y equal to log base a of x, remember that that means the exact same thing as writing x is equal to a to the power of y. That's because logarithmic and exponential functions are inverses of each other. So then we're just going to put together a few things from the previous two sections, and we're going to differentiate both sides with respect to x. So if we take the derivative of x with respect to x, that just leaves us with 1 on the left. And then if I take the derivative with respect to x on the right-hand side, here's where we can use what we learned about the derivatives of any exponential function. That's going to leave us with a to the y times the natural log of a. That's using the chain rule. And then also by implicit differentiation, we then also have to multiply by y prime, which is the same thing as dy dx. So what we get is that solving for dy dx, or y prime, this gives us dy dx is equal to 1 divided by a to the y times the natural log of a. And then since we had that a to the y was the same thing as x, that means we have 1 over x times natural log of a. So really what this last part is saying is, if we go back to the beginning, the derivative with respect to x of log base a of x is equal to 1 over x times the natural log of a. Even more important for our uses, something that we're going to use a lot more, is if we use base e. So if a that we've had in this whole conversation is really just the natural number e, we get that the derivative with respect to x of the natural log of x, because that would be log base e of x, that's equal to 1 over x. So what we have from all of this are these two facts. Let's take a look at an example. Differentiate f of x equal to log base 10 of the square root of x. So here we are going to use the chain rule because we have the square root of x function inside of the logarithmic function. And then we're also going to have to use what we just discovered, is that the log base a of x, the derivative of that, is 1 over x natural log of a. So here the base is 10. So if we want to find this derivative, f prime of x, we're taking the derivative with respect to x of log base 10 of the square root of x. So first we have the derivative of the outside function. And that derivative is just like what we see up above in the first thing that I boxed. This will be 1 over, not x, but the function that's inside. So square root of x. And then times the natural log of the base, in this case 10. And then by the chain rule, we have to multiply by the derivative with respect to x of what's inside. The derivative of what's inside is 1/2 x to the negative 1/2. We've seen that a few times before. And then we can simplify, since x to the negative 1/2 is the same thing as 1 over the square root of x. And I also have this 1 over 2. This is essentially just combining a few things in my denominator. So I would have 1 over the square root of x times the natural log of 10 times 2, and then times the square root of x. And you can see that really the square root of x times the other square root of x is going to give me x, and then I would have also multiplied by 2, and then also multiplied by the natural log of 10. So a good way to organize that would be 1 over 2x natural log of 10. All right, next example, let's look at a function that uses the natural log. So here, differentiate the natural log of the quantity x plus the square root of x squared minus 1. So first of all, by the chain rule, we would have the derivative of the outside function. And the outside function here is the natural log function. And so really the natural log function, back with what we saw before, its derivative is 1 over x. So with the chain rule, that just means I'm going to have 1 over everything that was inside the natural log function, just as it was written, x plus the square root of x squared minus 1. But then I have to multiply that, because of the chain rule, by the derivative with respect to x of x plus the square root of x squared minus 1. So now I have that fraction, and that's just going to hang out for the rest of this ride. And the derivative with respect to x of what's inside the parentheses there, I would first start with the derivative with respect to x of x. That's just 1. And then plus, now I have the square root of x squared minus 1. That again is going to use the chain rule. I have a square root function on the outside and x squared minus 1 on the inside. What we've seen with square root functions is that that turns into 1/2 times the inside raised to the negative 1/2. And then because of the chain rule, I have to multiply that by the derivative with respect to x of x squared minus 1. So now to clean this up a little bit, I still have my fraction 1 over x plus the square root of x squared minus 1, and then times parentheses 1 plus, if we want, we can write this as a fraction, 1 over 2 times the square root of x squared minus 1, and then times the derivative with respect to x of x squared minus 1 is 2x. Here we can see that we'll have a 2 in the denominator that will cancel with the 2 in the numerator. So this turns into 1 over x plus the square root of x squared minus 1 times parentheses 1 plus x over the square root of x squared minus 1. And again, we could simplify this by using some multiplication, but that would just involve the sum of two fractions, which may or may not be easier than what we're looking at here. So for our purposes, that's good enough. All right, so this next example is actually just going to be proving something for us that will then become useful a little bit later in this class. So the next example, find f prime of x if f of x is equal to the natural log of the absolute value of x. So first of all, we're going to use just a fact about absolute value that we've seen. So since f of x equal to the natural log of the absolute value of x is really equal to the natural log of x when x is positive, meaning x is greater than 0, and also that function is the same thing as the natural log of negative x when x is less than 0, we can differentiate each of those pieces. We can think of this as a piecewise function. So really we are thinking of f of x equal to natural log of x for x positive and natural log of negative x for x negative. So first of all, we already have that the derivative with respect to x of the first piece, natural log of x, is 1 over x. We already got that. By the chain rule, it follows that the derivative with respect to x of the natural log of negative x would be, first of all, 1 over negative x times the derivative of negative x, which is negative 1. So that gives us this first fraction, negative 1 divided by negative x. And then when you simplify that, you get 1 over x. So either way, the derivative is equal to 1 over x. So now we have this fact. The derivative with respect to x of the natural log of the absolute value of x is just 1 over x. So now an application of this new derivative that we've just learned, what's called logarithmic differentiation. So sometimes we may find it useful to apply logarithms to both sides of an equation before we actually take the derivative. And the reason why we would do that is because there are logarithmic laws that can help us. So first of all, we're going to use the natural log. So take ln of both sides and then simplify. So we're going to use all of those properties of logarithms to simplify. Then we will differentiate implicitly with respect to x, and then we will solve for the derivative of y, so y prime. So here's our first example. So we're first going to apply the natural log to both sides. So that just means natural log of the left equal to natural log of the right-hand side. So now the left-hand side is just going to stay as the natural log of y. But the right-hand side, here's where we can use a property of logarithms. We can take the power cosine x, and that becomes a multiplier. So we have cosine x times the natural log of x. Now that we have this simplified, you can see what we're going to do next. If we take the derivative with respect to x, we get to use the product rule. So the derivative with respect to x of the left-hand side, and then the derivative with respect to x of the right-hand side. So then on the left-hand side, we would have to use implicit differentiation. This turns into 1 over y. That's the derivative of the outside function, the natural log function. But now I have to multiply by y prime. That's the derivative of the inside. And then on the right-hand side, by the product rule, the derivative of cosine x is negative sine x. And then I have to multiply that by the second function, natural log of x. And then I have to add now the derivative of the second function. The derivative of the natural log of x is 1 over x. And then multiply by the first function, cosine x. So now I've used all of my derivative laws. All that is left is just solve for y prime, which would mean just multiplying both sides by y. So that means y times the entire right-hand side. And here I can simplify this a little bit. Negative sine x, natural log of x. And then times, this is cosine x over x. And since we had an expression for y, we should actually put that in to finish this. So then we can have the derivative all in terms of x. So since y is equal to x to the cosine x, then now we have an expression for y prime. Oh, that was a plus up there. So that's y prime. And we could distribute x to the cosine x. Nothing would simplify. That would just have x to the cosine x times both of those expressions there. So we can also just leave it factored out like this. All right, let's see one more example that we can use with this logarithmic differentiation. So here, this is a very complicated expression. And if we wanted to take the derivative of y with respect to x, we could use the quotient rule. So this is just really an alternative way of looking at this to see what we could get. So I'm going to write natural log of y equal to the natural log of the quotient e to the negative x cosine squared x divided by x squared plus x plus 1. And then the right-hand side, again by properties of logarithms, if I have a quotient inside, that turns into a difference of logarithms. So it's the logarithm of the numerator minus the logarithm of the denominator. And then now we take the derivative with respect to x. So the derivative with respect to x of the natural log of y. And then I'm just going to write the derivative with respect to x of the entire right-hand side. So then, as we saw before, the derivative with respect to x of the natural log of y is just 1 over y times y prime. And now, on the right-hand side, I have two natural logarithms, so those derivatives are already going to start with just 1 over what's on the inside. But then I have to multiply by the derivative with respect to x of what's on the inside. Notice how this is exactly like what I wrote on the left-hand side. 1 over something times the derivative of that something. So with this next logarithm, 1 over the thing that's on the inside, so 1 over something, times the derivative of what's on the inside. So I have 1 over y times y prime on the left. On the right, I have my fraction 1 over e to the negative x cosine squared x. And then the derivative, notice this is a product there, e to the negative x times cosine squared x. So the first derivative that I would have, I'd have e to the negative x. But that's going to use the chain rule, which means times the derivative of negative x, which is negative 1, and then times the second function in the product. And then by the product rule, plus, I'm still not done with this first derivative, the derivative of the second function, cosine squared x, that again is using the chain rule. That's a 2 times the cosine x times the derivative of cosine x. And then I have to multiply that by the first function. And then minus, I would have the fraction 1 over x squared plus x plus 1 times the derivative of x squared plus x plus 1. That derivative is just 2x plus 1, so I'm going to, because of space, write 2x plus 1. That's the derivative. And then over the denominator x squared plus x plus 1. All right, so now let's see if we can simplify some of this. One thing that we can actually notice from the first part of this sum here, you have an e to the negative x in the denominator. And then you have two products in that sum, and they both have an e to the negative x. So I have a common factor in the numerator and denominator, which means I can divide out by it. So what's left from that whole complicated expression up there turns into cosine squared x. Oh, but I have a negative 1, so times a negative. And then I've got 2 cosine x times negative sine x, so that turns into minus 2 cosine x sine x. And this is all being divided by cosine squared x. And then minus the second fraction, 2x plus 1 over x squared plus x plus 1. And you can also notice that there's a common factor again in that first fraction. I can divide everything by a cosine of x. So what I have is 1 over y times y prime equal to negative cosine x minus 2 sine x divided by cosine x. I can't simplify that any further because I don't have a common factor of cosine x in both terms in the numerator anymore. So all that is left is just multiplying both sides by y, which means I would have the whole right-hand side, negative cosine x minus 2 sine x divided by cosine x minus 2x plus 1 divided by x squared plus x plus 1. And that would have to be multiplied by y. So instead of writing y, I'm just going to write down the expression we had for y. E to the negative x cosine squared x divided by x squared plus x plus 1. And again, if we distributed, maybe there would be some simplification, but it would still be two pretty complicated fractions. So that's good enough for our purposes.